Okay, my name is Mahmoud Majid. Today I'm going to talk about our paper, Efficient Mean Estimation with Pure Differential Privacy via Software Scores Exponential Mechanism. This is based on a joint work with my amazing co-authors, Sam Hopkins and Gautam Kamath, who is also my advisor here at Waterloo. Okay, so let's begin. As you might have already guessed, our main contribution is a new way to design private algorithms efficiently. We call this new technique. Okay. Our main contribution is a new way to design private algorithms efficiently, and we call this new technique the software scores exponential mechanism. We specifically apply this new technique to mean estimation, but we anticipate that this technique would be applicable to many other problems as well. So hopefully by the end of this talk, you should be able to learn about this new technique and apply it to other problems in private estimation or differential privacy in general. Okay. So now let's define the main problem of our focus in our paper, which is mean estimation for high dimensional distributions. You have some vector mu in RD, which is hidden. You have some distribution with mean mu, and you take n samples IRD x1 to xn from this distribution. And your goal is to find some vector mu, some vector that approximates this mean mu. So there was an open question for a while that whether there exists an algorithm which is simultaneously pure differentially private, it has of the sample complexity, and it is polynomial time in the input size for this problem or not. And in our work, we answer this question affirmatively. Specifically, we give the first algorithm for this problem, which is simultaneously computationally efficient. It requires of the samples up to logarithmic factors, and it is pure DP. And as a bonus, we also get robustness and sub-Gaussian rates for free. One thing to note is that any 2 out of the 3 properties that I mentioned, it was known how to get any 2 out of the 3, but all 3 at the same time was an open problem. Okay, so now let's define private mean estimation a bit more formally. Again, as before, we have some distribution D. It has mean mu. We take n samples IID. We need to make an assumption about D, and that is it has bounded covariance. Let's say it has covariance bounded above y1. This is because otherwise, it can be shown that you can't do private mean estimation otherwise. And for technical reasons, in this talk, we assume that we have access to some rough estimate mu0, which has this sense at most of root D to mu. And our goal is to find some estimator mu hat, which can approximate mu up to error alpha with probability 1 minus beta. And also it satisfies pure differential privacy. Okay. Now, first I will tell you 3 algorithms for this problem that don't work. Then I will try to fix one of them. And in the end, I will explain our algorithm. Okay, so let's begin with 3 algorithms that don't work. The thing is that these 3 algorithms that I'm going to explain to you, each of them is like, each of them has a different issue. Each of them is flawed in their own way. Okay, so the first 2 algorithms are using the Laplace mechanism and using the Gaussian mechanism. These 2 are fairly simple. You just take n samples x1 to xn, you truncate to a ball of radius root D. This will limit the sensitivity. So now you can just take the empirical mean of discrete discrete points and add Laplace noise or Gaussian noise to it. Then this will give you a private estimate. The thing is, if you add Laplace noise, you're going to end up having the wrong sample complexity because of this discrepancy between L1 norm and L2 norm. And if you add Gaussian noise, you're going to get concentrated DP, which is qualitatively weaker than pure differential privacy. Okay, these are the first 2 algorithms. The third algorithm, which is more important, is using the exponential mechanism. The idea is very simple. We want to define a score function over our set of candidates, and then run the exponential mechanism to choose, to output an estimate for the mean. So we already have some estimate of root D of the point, so we have to look into the ball of radius root D in D dimensions, okay? Now, a standard way of designing a score functions for the exponential mechanism is counting the number of points you need to change in order to make that candidate point look bad. Now we have to define what bad means, but this is a recurring theme in using the exponential mechanism. Why this is good? Because the number of points you need to change has sensitivity 1. It has low sensitivity, okay? So now the problem is how we should define what it means for a point to be good or bad. If you, the intuition is that your candidate point has to be close to the true mean in every 1D direction. If it is close, it has to be close in every 1D direction. So a way you can define the score function is how many of the points of the input points you need to change in order to make that candidate point in the ball of radius root D in D dimensions look far in at least one direction. Now, the issue is that there are exponentially many directions in RD. So in order to compute this score function, previous works required exponential time. Another issue is that if you take a net over the set of candidates, which is the ball of radius R in radius root D in D dimensions, you're gonna end up having exponentially many candidates. But the good news is that your sample complexity is going to be okay. It's going to be O tilde of D. But as I said, there are 2 points in this algorithm where they cause the runtime to be exponential in the number of dimensions. Okay, so here are the 3 algorithms we have, like the algorithms prior to our work. As you can see, each of them have a different issue, and as you can probably already guess, our work gets all of the 3 De-Sitter deltas at the same time using a sum of squares exponential mechanism. Okay, now I'm going to explain how we can fix the exponential mechanism that I talked about right now. There were 2 issues with this algorithm. First one was that you are going to sample from an exponentially large domain. But so the more abstract question here is, when can you sample from the exponential mechanism efficiently if your domain is exponentially large? Okay. The second problem is we don't know how to compute the score function there because there are exponentially many directions. But this is something we have seen in efficient high dimensional statistics in recent years over and over again. So maybe we can use some of the developments from there in order to fix this issue. Okay. Now let's talk about the first problem. This is a very abstract problem. It is that we have a score function. We want to see whether we can do the exponential mechanism with the score function efficiently or not. Efficiently and privately or not, sorry. And hopefully, and fortunately, this problem has been studied before, specifically by Basili, Smith, and Thakurta in 2014, and by Mangubi and Vishnoi in 2021. Specifically, if your score function satisfies these 2 properties, that is, it is log concave with respect to the candidates, and it is Lipschitz with respect to the candidates, then we know that there exists some efficient sampler for the exponential mechanism. Okay, so now we know how we can deal with the first issue. We basically need to design a score function that is log concave, that is concave and Lipschitz. For the second issue, we can look into some of the recent developments in efficient high dimensional statistics. Specifically, we have seen in robust estimation, the same problem arises. You have exponentially many directions, but you can still compute the score function. In mean estimation for heavy tail distributions, we have seen this. And now we are seeing this in privacy for by us and in a concurrent work by Kothari, Marangesi, and Wellinger. Now let's, the most relevant of these body of work to ours is mean estimation for heavy tail estimation. Sorry, a mean estimation for heavy tail distributions. Now let's see how the algorithms in this line work basically. The main, at the heart of these algorithms is this definition called centrality or high dimensional median of means. Basically, you have some samples x1 to xn. You put them in you put them in k buckets. You compute the mean of each of these buckets and name them z1 to zk. And then you define centrality or what it means for a point to be high dimensional median for these points z1 to zk. Basically, you define a point to be a high dimensional median if and only if it looks like a median on any single direction. Okay. Now, a good lemma here is that, a nice property here is that the mean itself is going to be central with high probability. The true mean is going to be central. And also any central point is going to be close to this true mean with high probability. This is a really nice property. So we have basically characterized what it means for a point to be a mean in high dimensions. Now the thing is that this definition, centrality, can be also expressed as a quadratic program. I'm not going to explain this quadratic program, but conceptually what it does is that it searches over all of the directions in d dimensions and looks for the directions that are bad, the directions that this candidate point mu tilde doesn't look like to be a median. So basically, if this quadratic, if no such direction exists, then this quadratic program is going to have low value. And therefore, mu tilde is going to be a central point. But what if mu tilde is not a central point? Then, by definition, there exists some direction which is bad. Then there exists many of the projections. There exists many zi's on that direction which are on one direction, basically. Now, the thing is, if you take that direction, it should take you towards the central points. So basically, certificates of non-centrality take us to central points and ultimately to the mean. But the issue here is that this is not efficient. We don't know how to solve quadratic programs efficiently. It requires exponential time most of the time, but we know how we can relax them to semi-definite programs efficiently in a very standard way. But the thing is, if we relax this program to a semi-definite program, the semi-definite program is going to have the exact same properties that the quadratic program has. And now we can solve this SDP efficiently. And we show that if this semi-definite program has high value, and then if you take V, then V is also going to take you to the true mean. So now we know how to deal with the second issue as well. We can use SDP relaxations. So here's the final algorithm. You take the same semi-definite program we had before, and you want to, the goal is to define a score function over the set of directions. You want to take some direction, you want to move towards it to reach a central point. So you take the same semi-definite program, you add a new constraint that V is equal to Y. It is easy to show that this score function is going to be concave and Lipschitz. Therefore, by the results by Basile, Smith, and Thakurta, we can sample from this efficiently and privately. Okay, So now here's an animation of how the algorithm works. You start with some candidate point. You sample from the set of directions using the exponential mechanism. You take that direction, you take a step in that direction. You do this repeatedly until you reach a central point, okay? The thing is, what we did here is not specific to this problem at all. It's not in any way specific to mean estimation. So we can prove a method theorem here, basically. So if you have some score function that has these nice properties, it has that high score function implies high utility, it has bounded sensitivity, Lipschitzness, concavity, and it has a large volume of good points, then you can prove that the exponential mechanism will produce an epsilon dp high utility point efficiently. Specifically, SOS programs have some nice property that we can prove these properties for. And we prove that in our paper. You can look it up. It's a bit, there you go. Okay. And for coarse estimation, we also use from like going, as if you remember, I assume that we have access to some point that is distance root D. But in order to go from R to root D, we also use the SOS exponential mechanism, which we call the coarse estimation step. The thing is that that step isn't at the moment efficient, isn't optimal. So some future directions are maybe exploring more connections between robustness and privacy. This is, I think, one of the, this is a very clear connection that we established here. Basically the same tools that are used for robustness are now used for privacy. And maybe we can also explore where else we can apply this SOS exponential mechanism. So the final theorem is as follows. You can, it is like the guarantee we get is optimal in every term, except for this term, which is for a coarse estimation step. So it is an open problem whether we can get rid of that term or not. Thank you.